In the field of math called graph theory, we study these things called graphs. A graph is a structure made out of vertices and edges. Vertices are generally represented as dots or circles, and edges are lines joining pairs of distinct vertices. Today I'm going to tell you about an unsolved problem in graph theory called the Reconstruction conjecture, but in order to understand it, it's critical that you understand vertex deletion. It's common to name graphs. I'm going to name this one G, and it's also common to label the vertices of a graph. So I've labeled these vertices A, B, C, and D. Deleting a vertex from a graph causes the vertex to disappear as well as the edges that are touching it. So for example, if we deleted the vertex A from this graph G, we could write that like this, G minus A. So we're taking A away from this graph. And what will remain is all of the vertices other than A, and all of the edges that weren't touching A. So B and C, as well as the edge joining them, remains, and so does the vertex D and the edge joining that to C. What was deleted is A, as well as those edges touching A. One more example, we could delete the vertex C. That would give us G minus C. What would remain are the other vertices, namely A, B, and D, as well as any of the edges that weren't touching C. In this case, the only edge of the graph that wasn't touching C is the edge joining A and B. So that's how deleting a vertex works. When we delete a vertex, we delete it as well as the edges touching it. Alright, now you're ready for the fun part, which involves a deck of cards. You actually can't see these cards right now on account of the fact they're stacked in a deck, so it's a good idea to separate them. And we see that we have 5 cards all showing some graph. And now, friends, it's time to put on our detective hats, because what are these cards? They're actually the graphs that result from deleting the individual vertices of some mystery graph. For example, remember the original graph we looked at. If we deleted A and then put this resulting vertex deleted graph on a card, and then deleted C and put this vertex deleted graph on a card, and did the same thing with B and D so that we had a deck of vertex deleted subgraphs, they're called. That's what this is, but for some mystery graph that we don't know. Now, what sort of things do you notice looking at these cards? You might notice that 1 and 2 are the same graphs. They have the same structure. We say that they are isomorphic. So even though they might be different graphs, we could give them different names and label their vertices differently, their structures are the same. Same thing with card 3 and card 4, those graphs are isomorphic. You might also notice that all of these graphs are connected except for this one on card 5. Of course, a graph is connected if it's possible to travel between any pair of distinct vertices. This graph is disconnected because we can't get from here to here or from here to here. The more important thing I want you to notice is that all of these graphs have 4 vertices. So the mystery graph that these come from has how many vertices? The answer must be 5. We know that for 2 reasons. 1, each of these graphs results from deleting a single vertex from the mystery graph. If deleting one vertex results in a graph with 4 vertices, then of course the original mystery graph must have had 5 vertices. On the other hand, for every vertex that we delete, we get a subgraph. In total, we have 5 subgraphs, so there must be 5 vertices that we had a chance to delete. The number of vertices that a graph has is called its order, so we can start to put together our case file for this mystery graph. The first thing we know is that its order is 5. That's its number of vertices. Since we were able to look at the deck of vertex deleted subgraphs and determine the order of the original mystery graph, we say that the order is recognizable. Just from the vertex deleted subgraphs, we can recognize that the order of the original graph must have been 5. Now, just like there's a term for the number of vertices in a graph, there's also a term for the number of edges. For example, this vertex deleted subgraph on card 1 has 1, 2, 3, 4 edges. That's called its size. So can we recognize the size of a graph from its vertex-deleted subgraphs? Well, not necessarily. For example, here is a deck of vertex-deleted subgraphs, just 2 in this case. So how many vertices does the original graph have? Well, it would have to be 2. When we delete one vertex, we get this subgraph, and when we delete the other, we get this subgraph. Unfortunately, we don't know exactly how many edges the original graph had just from this information. Because, for example, this graph has 1 edge, and this would be its deck. If we deleted this vertex, we would just be left with this, and if we deleted this vertex, we would just be left with this. But there's another graph for which this is true, namely this graph. For this graph, this is again its deck. If we deleted this vertex, we'd have this remaining, and if we deleted this vertex, we'd have this remaining. So we don't know, does the original graph have 1 edge or 0 edges? It's not possible to determine this. So that's the bad news, but the good news is this is the exception, not the rule. As long as a graph has at least 3 vertices, it is actually possible to determine how many edges it must have from its deck. Now let's see how that's done. Let's say we have a graph called G, and it has at least 3 vertices. N is a common letter to denote the number of vertices, so we'll say N is at least 3. And then the size of the graph, its number of edges, we'll say that's M. And we're going to try to figure out M from the deck of G, that is, those cards consisting of its vertex-deleted subgraphs. Remember, G is a graph, so it's made up of vertices and edges. We'll call the set of its vertices V, and since it has n vertices, we'll name them V1, V2, all the way up through Vn. It's necessary to put this arbitrary labeling on the vertices just for the argument, but keep in mind, in general, when we're looking at these decks, the vertices are not labeled, and if they were, the problems we're discussing would be pretty trivial. Now, if these are the vertices of G, then the deck of G consists of all of those vertex-deleted subgraphs, G minus Vi, where I ranges from 1 to n. Let's say that each of those graphs, G minus Vi, has a size of Mi. So Mi denotes the number of edges in the vertex-deleted subgraph G minus Vi. And keep in mind that this information is accessible to us. We can look at the deck of cards and count the size of each vertex-deleted subgraph. So then, how can we tie this information we know to this information we want, the size of the mystery graph? Well, think about this. What happens if we add up all of those sizes Mi? So we're going to add Mi from I equals 1 all the way up to n. Of course, there are n cards in the deck because G has n vertices. Well, certainly every edge, let's say E for just a general edge, every edge E in G is going to be counted in a vertex-deleted subgraph G minus Vi unless Vi is touching E. If Vi, the deleted vertex, is touching E, then E would be deleted along with the vertex. But keep in mind also that each edge is touching exactly 2 vertices. That means that every edge of G is going to be counted in every term of this sum except for 2. For example, if we were to consider all of the vertex-deleted subgraphs of that original graph G we were looking at, the edge joining A and B would appear in all of them except for G minus A and for G minus B. For example, here in G minus A, this edge is gone because we've deleted a vertex that's touching it. But in G minus C, we still have that edge because no vertex touching it has been deleted. So every edge of G is going to be counted in all terms of this sum except for 2 of them, that is n minus 2 terms total. Hence, this sum must equal n minus 2 times m, the number of edges in the mystery graph G. And as we already discussed, order is recognizable. We can figure out n from the deck of G. So we know this, so all we have to do is solve for m. Dividing both sides by n minus 2, we then find that the size of the original graph can be found by just adding up the sizes of the cards in the deck and then dividing by n minus 2. Of course, this division emphasizes the fact that n has to be at least 3. Alright, let's try this calculation with our deck of cards. So to find the size of our mystery graph, we first need to add up the sizes of the cards in the deck. The size of this card is 4. This one is also 4, this one is 3, this one is 3, and this one is 1. So in total, 4 plus 4 plus 3 plus 3 plus 1. We then have to divide by the order minus 2, that is 5 minus 2, which is 3. This comes out to 15 divided by 3, and so the size of the mystery graph is 5. Now that we know the size of that original mystery graph, we can also easily figure out something else important about it, and that is its degree sequence. Let's briefly return to our original graph to clarify this term. The degree of a vertex is the number of edges it is touching, so the degree of A here is 2, the degree of B is 2, the degree of C is 3, and the degree of D is 1. If we then put these degrees in sequence, we have a degree sequence of the graph G. Although traditionally the degree sequence is made unique by writing it in non-increasing order. So in this case, that would be 3, 2, 2, 1. Determining the degree sequence of our mystery graph from its deck of vertex-deleted subgraphs is actually really straightforward. Keep in mind that we've notated the size of each card in the deck as mi. And each time we delete a vertex, vi, we're also removing precisely the edges that are touching vi, the number of which is, by definition, the degree of vi. Hence, the degree of any vertex vi, which is denoted deg of vi, can be found by just taking the size of the original graph, which we know we can figure out, and subtracting the size of g minus vi. Because the difference between m and mi will be exactly the number of edges which are removed when we delete vi, which is of course exactly the number of edges touching vi, hence the degree. So to find the degrees of the 5 vertices in our mystery graph, all we need to do is take the size and one by one subtract the sizes of the cards. 5 minus 4 gives us a degree of 1. 5 minus 4 gives a degree of 1. 5 minus 3 gives a degree of 2. 5 minus 3 gives another vertex of degree 2. And then 5 minus 1 gives a vertex of degree 4. And then we may like to just write this in non-increasing order. So 4, 2, 2, 1, 1. Alright, good work, detectives. We've now built quite a case on the original mystery graph. We've recognized its order, its size, and its degree sequence from this deck of vertex-deleted subgraphs. But can we now reconstruct the original graph exactly? The answer, of course, is yes. And at this point, it's very easy. Just consider this, card 1. This has a vertex of degree 3, which in the original graph must be the vertex of degree 4, because certainly in the original graph, its degree is either 3 or bigger, which means that it must in fact be 4. This means that the original graph, of course, has one additional vertex, and that vertex must have an edge joining it to this one. But if we add that vertex and edge, we will satisfy all of these properties. We'll then have that extra vertex of degree 1 that we need, and all of the other degrees are already satisfied. And hence, our suspect is fully identified. The mystery graph looks exactly like this. You can see that this graph satisfies all of the properties we've so far deduced. It has 5 vertices, 1, 2, 3, 4, 5. 5 edges, 1, 2, 3, 4, 5. And what is its degree sequence? It's 4, 2, 2, 1, 1. From here, a natural question follows. That is, would it be possible to reconstruct a different graph, one with a structure different from this one, that has these cards as its vertex deleted subgraphs? The answer in this case is no, but the question in general is one of the biggest unsolved problems in graph theory. This is the Reconstruction conjecture, often simply abbreviated RC. It says that two graphs of degree at least 3 that have the same deck must be isomorphic. This means that if two graphs have exactly the same vertex-deleted subgraphs, that is, the same deck, then the two graphs must in fact be the same. They have exactly the same structure. That's what isomorphic means. Said differently, this conjecture means that it's not possible to take a deck of vertex-deleted subgraphs and from it construct two distinct graphs that have that deck. This conjecture was made in 1941. It's generally attributed to Paul Kelly and Stanislaw Ulam. Ulam is well known for his work on the Manhattan Project at Los Alamos and for inventing the Monte Carlo method, as well as a bunch of other notable achievements. But now, over 80 years later, this is still an open question. Nobody has proven the Reconstruction conjecture. To disprove it would require finding two graphs that are not isomorphic, but that have the same deck, the same vertex-deleted subgraphs. Despite this conjecture still not being settled, there is in fact also a stronger form of the conjecture that is another open question. Remember, in our deck, we had a couple of graphs that had the exact same structure. Cards 1 and 2 were isomorphic, and cards 3 and 4 were isomorphic. So one might ask, what if we didn't have that extra information of these isomorphic subgraphs occurring twice? What if we only knew the non-isomorphic vertex-deleted subgraphs? Thus, the deck would only have 3 cards in this case. Well, is it still possible to reconstruct the original graph? It's not possible in general. Let me show you a counterexample with 3 vertices. Let's say we have a deck and these are the cards. One card has this vertex-deleted subgraph, and the other card has this vertex-deleted subgraph. Remember, in this context, we're only shown the non-isomorphic cards, which means that either of these cards may occur many times in the deck, but these are the only non-isomorphic vertex-deleted subgraphs. One possibility for the original graph that has this deck is this graph here. You can see if we delete this vertex, we'll get this card, and if we delete either of these vertices, we would get this card. That means that this card would appear in the deck twice if we were including all vertex-deleted subgraphs. The trouble, of course, comes from the fact that there is another graph, a distinct one, that has this deck of non-isomorphic vertex-deleted subgraphs. If you look at this green graph here, we can see that deleting either of these vertices would give us this card, while deleting this vertex would produce this card. If we knew how many times each of these cards appeared in the deck, we'd be able to uniquely reconstruct either this graph or this one. But without that information, it's not possible to uniquely identify the original graph. Hence, for this stronger form of the Reconstruction conjecture, where the deck only has non-isomorphic subgraphs, we restrict n to be at least 4. And under those conditions, it is again still an open problem. The Reconstruction conjecture has been affectionately described as a disease. Many people have taken cracks at it, and a lot of interesting progress has been made, including proving the validity of the conjecture for various families of graphs, such as the regular graphs. A regular graph is a graph whose vertices all have the same degree, like this one here, where every vertex has degree 2. It's fairly easy to see why we'd be able to reconstruct regular graphs. We know that we could find the degree sequence from the deck of a regular graph, and when we see the degree sequence is just one number over and over again, we'd know that we have a regular graph on our hands. From that information, we could look at any card, add in the missing vertex, and then figure out which vertices it needs to be joined to correct the degrees, so that we get the regular graph back. The Reconstruction conjecture has also been proven for disconnected graphs. Disconnected graphs are made up of what are called components. They have 2 or more separate components. And you can imagine that with disconnected graphs, the deck gives us a ton of information, because as long as we're deleting vertices in one component, all of the other components will be completely visible. Another interesting thing that has been proven concerning RC is that if we take a random graph on n vertices, the likelihood that it can't be reconstructed from its deck approaches 0 as n gets arbitrarily large. So that's the reconstructor conjecture, one of graph theory's biggest unsolved problems. For kicks, let me give you one more deck of cards, and you can try to figure out the order, size, connectivity, whether it's connected or not, of the original graph. And of course, try to construct the original graph in its entirety. Let me know what you think the original graph is down in the comments. You could describe your answer by just picking one of these cards and describing the missing vertex to create the original graph. And hey, if you enjoyed this video, consider supporting the channel by joining as a channel member. You can get early and exclusive access to additional videos and lots of original music too. I will sing my heart out for you. So let me know in the comments if you have any questions, and be sure to subscribe for more of the swankiest math videos on the internet.
From my fate, twisting to escape this. Cutting out of my wrist if you can break it. Breaking in my past, I'm making it up fast. So slow down, give me the time so I can fake it. Embrace the tune of words and just how I say shit. And let me speak my poetry to your face. It's not in the mid if you ain't listening. Not infinite if you ain't really in it.